We're starting to talk about different classes of chemical reactions. We've taken a little bit of time to talk about combustion reactions, where we have a fuel reacting with oxygen to make carbon dioxide and water. And one of our next classes of reactions that I'm going to spend some time talking about is precipitation reactions. We've already seen these a lot of times. So in a recent video on balancing equations, I had you pay attention to a reaction that looked something like this. Okay, so this was a reaction where we have silver nitrate reacting with calcium iodide to make calcium nitrite and silver iodide, and when we balanced it, we saw we needed 2 silver nitrates and 2 silver iodides. So it was a really straightforward reaction for us to do, and one of the things that I drew your attention to about it is I want you to pay attention to what's happening here with the phases. So we have 2 systems that are aqueous, that means these are dissolved in water. And then in our products, we have one that is aqueous and one that is solid. So we go from a reaction where we have 2 containers and they both look like probably clear colorless solutions. And then when we pour them together, then they make a precipitate. And most of the time it doesn't actually look like a solid, it just looks cloudy. So usually a precipitate looks like a very fine cloudy suspension in the water. But it counts as a precipitate. So if you started doing some qualitative reactions where you're looking to see where precipitations take place in the lab, this might be one of those ones that you're doing. So when we have this reaction where we go from all aqueous to something that has a solid, this is a precipitate. And note another thing about these compounds. Metal, nonmetal, metal, nonmetal, metal, nonmetal, metal, nonmetal. These are all ionic compounds. And here's the thing about ionic compounds. Well, first, I would suggest that you take a second, since we need to review our ionic, what our ions are and what our polyatomic ions are. Take a minute for yourself and just write down what the charges are on the ions and what the names are on the ions, just to make sure that that information is fresh for you. So the other thing that I want you to know is that ionic compounds, these are happening because we have charged particles, right? We've got a cation and we've got an anion. And we know that opposite charges attract. This is described by Coulomb's law. And you don't need to remember the exact details of the law, but what the law says is that larger charges have a stronger force of attraction. So that means if you have, like +2, -2, this is going to be a stronger charge combination versus +1, -1. And same with like +3, -3. And that charges that are closer together have a stronger force of attraction too. And you don't really have the tools yet to know whether or not our charges are closer together, so I mainly want you to think about this first one when we're starting to look at ionic compounds, because it turns out that the ionic compounds some are soluble in water and some aren't. Probably most of them aren't. So when you have an ionic compound like sodium chloride, table salt, you know that when you put table salt into water, I guess I should not draw it that way. I'll just draw it with a plus. That what happens is the table salt is going to dissolve. And so we would write NaCl aqueous, and if we were balancing it, we would just write the water again. And in reality, anytime you have an ionic compound that is dissolving, what it really is it's dissolving into its component ions. So if I drew a little schematic here, this initial thing would have some NaCl down here in the bottom. And then let's say we stir it, right? Stir it around. You will not see that solid sitting down there anymore. Instead, we will have sodium ions and chloride ions that are dissolved and dissociated from each other inside this water. So here's the important thing to remember about ionic compounds. If an ionic compound is soluble, it will dissociate into its ions in water, I should say. If it's soluble in water, it could be soluble in something else. It will dissociate into its component ions. So this is part of why it's important for you to know what your polyatomic ions are and for you to know what charges all of the things have. Let's look at another example. Calcium carbonate. This is the major component in chalk or in limestone. So let's refresh. If you have some limestone and you chuck it into a glass of water and then you stir, what happens? Yeah, not very much, because calcium carbonate is not soluble. So there is no reaction here, and that's probably what we would write, NR, for no reaction. Nothing happens when you put calcium carbonate in water because calcium carbonate doesn't dissolve in water. So some of these situations, you'll have an insoluble compound, and if you have an insoluble compound, well, that's just how it is. It's not soluble in water. You can get it to react with something else, but it's not soluble. But when you mix components together and then they form a precipitate like they did here at the beginning, this is a precipitation reaction. That you go from things that are soluble in water to something that isn't soluble in water, and then some stuff that is. So if we think about what's happening here in this solution of silver nitrate, I have dissolved silver ions and dissolved nitrate ions. And here I have dissolved calcium ions, and I have dissolved iodide ions, and I'm not going to worry about balancing them right now. And now in this solution, this solid down here, this is the AgI. And here in solution, I still have calcium ions, and I have nitrate ions. But the silver iodide has precipitated out and is not in the solution. Okay, so what you need to know in order to predict the reactivity of ionic compounds on whether or not they'll make a precipitation is you need to know solubility rules. And yes, these are more rules that you're going to have to remember. I'm going to try and make it as straightforward and organized as possible. So I'm going to have 3 classes. I'm going to have my things that are soluble, always. And then I'm going to have my things that are mostly soluble. And then I'm going to have my things that are mostly not soluble. Okay? So my mostly soluble has 2 categories. Or my totally soluble, sorry. My totally soluble is that if the cation is Na plus, K plus, NH4 plus, and I'm going to put and lithium with one exception, then the compound is soluble. So guess what? Lithium, sodium, potassium, these are all our alkali metals. They're all in that first column of the periodic table. They're all grouped together, plus ammonium. So these guys are going to be really easy for you to remember. If you see any of these cations, I think lithium has one exception, so that's why it's in parentheses. But if you see any of these guys, it does not matter what it is attached to, that compound is soluble. We also have a couple of anions, where if you see that anion, it's soluble. So if the anion in the compound is nitrate or acetate, then the compound is soluble. You don't have to have both of these to be true, you just need one. Right? So if I say nickel nitrate, it's got nitrate in it. It's soluble. If I say silver acetate, it's got acetate in it. Silver might be a bad example, actually, but it's insoluble with a lot of things that are otherwise soluble. But anyway, we're going to just roll with it. If I say calcium acetate, it's soluble. If I say lead nitrate, it's soluble. If I say sodium sulfide, it's soluble. If I say potassium hydroxide, it's soluble, right? Any of these that have one of these 5 groups, possibly the 6th one, then it's going to be fully soluble. So that's our soluble group. Our next group is the mostly soluble. Maybe I should put lithium over here, but I didn't have any other cations, so it's going to hang out. So the rest of these rules mostly are looking at the solubility of anions, okay? So my next group is going to be most of the halides: chloride, bromide, and iodide. Fluoride has more things it's not soluble with, so it's not going to be part of this group. So this is always soluble except with silver ion, lead plus 1, and Hg2 2+. So we have a halide group for solubility. And then we've got sulfate, which is soluble except with barium, lead 2+, calcium, and strontium 2+. Now, if you are trying to figure out how you're going to remember these exceptions, these ones I don't really have a very good pattern for you. Silver, lead, and mercury are not too far away from each other on the periodic table, but check out barium, calcium, and strontium. Go find them on the periodic table. They're all together. And then you can just throw lead in to remember, okay? So that's our mostly soluble group. That means that if we have one of these anions, it's probably soluble unless it's one of these exceptions, okay? And then I have a class of my insoluble ones, which really is mostly insoluble, okay? Because again, remember my soluble cations and anions? If the cation is this group A right here, then even if this anion is insoluble with everybody else, it's going to be soluble if it's one of those group A. So I've got 2 sets of anions that we're going to take a look at that are almost always insoluble. So carbonate was one of those, and phosphate is the other one. These are insoluble. Sorry, that doesn't start with an I. Now we're ready. Insoluble. except with group A. Okay, so if it's one of these cations, then it's going to be soluble anyway. Otherwise, it's not soluble. Our other group of anions are hydroxide and sulfide. These are also insoluble, but we have a couple more exceptions besides for just these group A. So this is except with group A, with strontium, barium, and calcium, which are all together on the periodic table, right? These are all group 2. So group 1 and group 2 elements, these ones are going to be soluble with hydroxide and with sulfide. So this is not too many to remember. Of course, there are a few different ions that I could bring in here. There's certainly more anions. There are certainly more compounds that could be insoluble, but I'm not going to hold you responsible for remembering all of them. I just want you to remember this list because these are some of the most common ions that we ever do stuff with. Okay. Now, this list, you don't have to go back in the video and write them all down because our next worksheet or our current worksheet has all of these together on one little table on it so that it's easy for you to remember. So it's right at the beginning of this week's worksheet. All right, so what do we do with this kind of information? What we do is we predict products of reactions. Okay, so we might say something like, if we mix together sodium chloride and potassium hydroxide, what happens? So right now, the only kind of reactions we know about are combustion reactions and precipitation reactions. Okay, we're going to build to our list, but right now this is what our tools are. So we look at this and we say, is this a combustion reaction? No. There's no oxygen in here. We're not burning fuel, so it's not a combustion reaction. But is this a precipitation reaction? Well, let's look. This looks like an ionic compound, metal, nonmetal. This is an ionic compound, metal, nonmetal. Okay. So think about what happens if I were to swap partners for the cations and the anions. All right. Here are my cations and my anions. So if I were to swap these, then rather than sodium being with chloride, sodium would be with hydroxide and potassium would be with chloride. So now we check our little list of solubilities and we say to ourselves, oh, look, sodium and potassium, these guys are both group 1. These guys are soluble with everybody. Chloride is soluble with most. I mean, we could stop right there, right? But I'm just being complete. And hydroxide is mostly insoluble, but these are both group what? Group A, right? And so my conclusion is there is no reaction. Sodium chloride and sodium hydroxide are both soluble. Potassium chloride and potassium hydroxide are both soluble. These guys will all just hang out in solution together and just sit around. And sometimes that's the answer, no reaction. So let's try another one. What about silver? Oh, excuse me, not silver. I didn't want to go there yet. Plus we just saw silver. We'll do aluminum nitrate. What happens here? Well, what's our process? Let's look at our ions. Al3 plus and NO3 minus. Nitrate is one of those guys who's soluble with everybody, so this is aqueous. Oh, I should have put these. I did. There we go. Sodium hydroxide we just looked at. We know that sodium is +1 and hydroxide is -1. So when we recombine these, we would swap partners. Al3 plus would now be with hydroxide, and sodium would be with nitrate. So I can see that both sodium and nitrate, these guys are soluble with all. But I don't have any special rules covering aluminum. And I know that hydroxide is insoluble with most things. So I'm going to then conclude that the aluminum hydroxide will form an insoluble compound. So what kind of compound will it make? Well, we can see that hydroxide has a -1 charge and aluminum has a +3 charge. So that means we're going to need 3 of those hydroxides. And this will be insoluble. And then the sodium nitrate will hang out in solution. So my balanced equation would need 3 sodium hydroxides and 3 sodium nitrates to be balanced. And here we go. We have made a precipitation reaction. So we can use those solubility rules to predict what the products are of reactions and whether or not a reaction actually occurs. Let's try a couple more examples. Okay, in my first example, let's combine calcium sulfate and potassium carbonate and see what happens. And in the second example, let's combine magnesium bromide and silver nitrate. So I want you to go look at your solubility rules, predict whether or not we're making any insoluble compounds, and also put the phases everywhere and balance it. So let's see, we'll say soluble or not. That's one of our things. We're going to add phases and we're going to balance if anything happens. Okay, so pause the video and give this a try, and then come back and we'll check our work. Okay, let's find out what happens here. So I'm not always going to take the time here and make a big process out of these ions. I might just put +2, -2 over so I can see what kind of ions. Oops, I don't have 2 pluses. That would be silly. All right, so hopefully you found that these are both soluble, but that when we add calcium and carbonate together, this will make a precipitate. And then our potassium sulfate will still be soluble for both potassium because it's soluble with everybody, and sulfate is soluble with most things. And it's already balanced, so we don't have to do anything else. Okay, next reaction. Put my charges in, +2, -1, +1, -1. And I know that nitrate is soluble with everybody, and bromide is soluble with most except for things like silver, so it turns out this one's soluble too. Speaking of silver, we have silver right here, so silver and bromide are going to make an insoluble compound. And then magnesium and nitrate are just going to hang out in solution. And I can see that I've got 2 bromides here, so I'm going to need 2 here, and that means I'm going to need 2 here, and now it's balanced. And this should be aqueous. All right, so hopefully you were successful at both detecting whether they were soluble, adding the phases, and balancing all of these. And the other thing that I want to mention here, where we have our partners swapping places. So if these are my blue and these are my red, then they've swapped partners, right? You may or may not see this also referred to as a double displacement. I've heard this term a lot. I don't think it's very useful because it just tells us that we're swapping partners. It doesn't tell us whether we have a precipitate. It doesn't tell us what else is going on. But I wanted you to be familiar with this term. If you do see a double displacement, it is a situation where we have swapped partners, where both the cation and the anion swap partners. All right, so you should be all set now for practicing predicting products and solubility, and be ready to do the next step, which is going to be to combine some of our molarity calculations with these precipitation reactions. So that's what's coming up next.